3, 2, 1, pressing live.
Okay, hi everyone. Welcome to this week's Earth Science Research Group seminar. Thanks for coming. If you're watching on YouTube, please feel free to put some questions in the chat and we'll try and ask them at the end if there's time. And yeah, I'll hand you over to John now, who's going to introduce today's speaker.
So, hello everybody. Hello everybody in Liverpool, and also people who are on YouTube, who I can't see, but you're very welcome here. So I'd like to introduce Thomas Ferrand, and his history in brief is he did his master's in geophysics engineering in Strasbourg, and then he has another master's degree in geology from Nancy, and then he did his PhD in the École Normale Supérieure in Paris. Forgive my pronunciation. This is where I met Thomas the first time, and he was working then on experimental reproduction of mantle earthquakes, basically. And then he's had some postdoctoral positions, first in the Earthquake Institute in Tokyo, and then in the Scripps Institute in San Diego in the US, and then in now he's in Orléans as a postdoctoral fellow working in the laboratory there. So he's going to tell us about deep transformation-induced earthquakes. Please go ahead, Thomas.
Thank you, John. Thank you, Caitlin, Janin, for your help. Thank you for the introduction. So I will talk about basically 70% of what I've been doing for the last 8 years. So deciphering transformation-induced earthquakes from the lab to the field and from slabs to atoms. First, before I show everything, I want everybody to be aware that this is not, that I did not do it alone. There are many people I have to thank for different parts of the project, the projects that were going on. So first, I will tell a story about focused on the lower Wadati-Benioff plane of seismicity, and step by step I will broaden the scope. You will see. So here is a profile, a well-known profile, Northeast Japan, where you see a thermal model published by Peacock in 2001, and with the well-known double seismic zone, composed by two planes of seismicity, plus some earthquakes in between. So you can see at first order that the lower Wadati-Benioff plane is located somewhere between the 400 and 800 isotherms. So that's why a number of researchers have proposed that this lower Wadati-Benioff plane was actually the dehydration isotherm of Antigorite, which is the serpentine high temperature variety. And actually this is wrong. And in the same time, they were not that wrong. So as you can see, these two planes are separated by about 40 kilometers in Japan, but it can be 10 kilometers to about 40 kilometers, depending on the plate age. This has been shown at first by Hasegawa in 1994. And then several studies have shown that the double structure was a global feature, and especially Brzezinski in 2007, and more recently Ferrand and Prieto. And so you see that these planes merge at depth, and that around 150 kilometer depth here, you cannot define a double zone anymore. And this depends on the thermal parameter of the subduction. The upper plane, I will talk about it later, is very close to the oceanic crust, if this exists, or at least the uppermost mantle. And it's very close to the subduction interface. And so that's why it's easier to imagine that earthquakes occur there, which is not actually that easy to imagine when you do a basic rock deformation in the lab, because normally the pressure at high pressure, let's say at 40 kilometer depth or more, which means more than 35 kilometer, which means more than 1 or 1.5 GPa, normally the ductility of the materials, due to the confining pressure, does not allow dynamic ruptures to nucleate if you have a homogeneous and relatively stable system. And so we won't talk today about equilibrated systems and stable systems. We will talk about unstable things. So the upper plane and the lower plane is in the mantle, in the middle of the peridotite, at least as far as we know. There, the composition of the rock should be much easier than for the upper plane, which could be mantle rocks, crustal rocks, or even subduction channel mixture. So let's be happy to talk about the lower plane at first. So the lower plane is earthquake population occurring in mantle, which is peridotite, and so mostly olivine, which is oxygen, silicium, magnesium, and a little bit of iron. Okay, and when you put some water in it, let's say about 12%, you can make serpentine minerals, and especially, so this is the formula of the general formula of serpentine minerals, but the actual composition of Antigorite is somehow more difficult, and this is actually the composition here for M, so the modulation of the period of the mineral lattice. When it's equal to 17, it means that you have along the A-axis here 17 silica tetrahedra, and this can be 15, this can be 20. You have many possibilities because this M can vary between 13 and 24 as far as we know. So here is a pressure temperature diagram showing the stability field of Antigorite in the magnesium silicium hydrogen system. So as you can see, between 1 and 4 GPa, so about 35 to 120 kilometer depth, which is where the double seismic zone is defined. You can see that the dehydration of Antigorite occurs at around 550 degrees in water unsaturated conditions to form olivine, a talc-like phase, this is a hydrated high pressure talc, plus a little bit of water that is released at that moment. And if the system is saturated in water, then the dehydration occurs at much higher temperatures, around 650 degrees C. So as you can see, this is not far from isotherms if you stay around 2 or 3 GPa, but most of the time this is not. That's why. And so at a high temperature, the system is composed of pyroxene, so the enstatite, forsterite, and so this olivine, and water. And when you add on it the seismicity sorry, step by step. If you consider a system that is saturated in brucite, which is the magnesium hydroxide, then the destabilization of Antigorite occurs at much lower temperatures, between 450 and 500 degrees. And this is not the first complexity that I will add to the system, but let's wait a little bit. When you add on it the pressure and temperature conditions for hypocenters, you can see some correlations, incomplete correlations. This was the work from Abers in 2013. This is a key publication from which a large part of my work is based, actually. So here you can see for the Tohoku region that the pressure temperature conditions for hypocenters within the lower Wadati-Benioff plain are significantly denser. You have a larger population of earthquakes in the instability field. In the pressure temperature conditions in which we expect Antigorite to destabilize. And when you look at the same for Hokkaido, it's a little bit more obvious, I would say. And you can do the same for Cascadia, Tokai, and Kii. And I will show it later for Chile and for Romania. So the question from this is, what is the link between dehydration, the destabilization of this hydrous mineral, and the earthquakes? And the question that we can address in the lab is, how do we trigger intermediate depth mantle earthquakes? So what I did during my PhD, I took San Carlos olivine and Corsica Antigorite. I used very fine powders, micrometric powders, and I cooked it during about 10 hours at 500 degrees and 1.5 GPa. And then I did different mixtures to get aggregates with Antigorite fraction between 0 and 50%. And these samples made with a piston cylinder were 2.1 millimeter thick and the height of it was 3 millimeter. And this was the design for the synchrotron experiments, in between two gold foils here and in a tiny jacket of hexagonal boron nitride. You have the sample, and around it you have a graphite furnace to control the temperature, a cube of boron epoxy to control the pressure, and alumina pistons to apply some differential stress. We used diffraction radiography, X-ray radiography to get the strain and strain rate during the experiment, and X-ray diffraction to get the lattice distortion, so the elastic strain seen by the olivine crystals, and so to some extent the stress. This is so these experiments were made in a DDIA apparatus. I forgot to say it. In the synchrotron of Chicago, to get the high energy X-rays. So these are the results for a confining pressure of 1.1 GPa, which means the beginning of the lower Wadati-Benioff plain, around 40 kilometer depth. You have the stress as seen by olivine crystal lattice, and the cumulative acoustic emission recording as a function of strain. Because I forgot to say also that we had acoustic receivers between each of the anvils shown on this sketch. So when you have only olivine, you see that you increase the stress when you increase the strain, which is what you expect. And then when you start to increase the temperature in gray here, you start to release the stress slowly, which is the normal expected thermal relaxation. And when you do the same experiment with 5% of Antigorite in it, you observe a lower stress state on overall, and kind of the same response at the sample scale, right? But when you look at the cumulative acoustic emissions, you see that there is a burst of dynamic failures that occur when you cross the reaction noted 2 here at 640 degrees, which corresponds to the destabilization of the Antigorite breakdown. So when you then do the same experiment with 20% Antigorite, you have the same sample scale stress strain relation, but no acoustic activity at all, which is one very, very clear example of something very important, which can be described as force chains or stress percolation. Or what I want to say is that the deformation style and strain localization processes are scale dependent, and that the same behavior at the kilometric scale, for example, or at the millimetric scale in these experiments can actually hide very diffuse or very localized deformation at a scale that is 1,000 times smaller. So these were the results at 1 GPa, and this is the same at 3.5 GPa. And here you see that you have acoustic activity in every experiment, and you see a very, very nice stress drop in the red curve here with 50% of Antigorite, because you have a connected, if you have 50-50, you necessarily have some a connected Antigorite network from the top of the sample to the bottom. And so when you destabilize it, you necessarily see it on the stress strain curve at the sample scale. And regarding the blue curve, and we have questions on it, of course, as usual. We have acoustic activity only when we have a really high differential stress applied to the sample before, just when we start to increase the temperature. So, and then the microstructures don't look the same. So this is a summary of the experiments. On the pressure temperature diagram, you can see that at 1 GPa, we have a lot of acoustic emissions only with 5% Antigorite, and only when we are outside the stability limit of the stability field of Antigorite. And you can see that the process is more progressive and occurs with more with a larger range of Antigorite fractions at higher pressures. And this is the natural seismicity for you to compare with the experiments. So the conceptual model, as you will see here now, when you increase the Antigorite fraction in dark green, you decrease the size of the Antigorite free volumes, which I call the asperity size in the end, and you increase the size of the cluster length, the Antigorite clusters. So if you plot a length as a function of the Antigorite fraction, this is the asperity length. This is the cluster length. So this is the result from the percolation theory. And you need a third length to close the this triangle I tried to draw, and this is the fracture nucleation length, which is basically a rupture criterion, but as a length, and you can see that this is so. You have the rigidity of the material multiplied by the rupture energy. So I mean the rupture criterion actually, and you divide it by the shear stress, and there is a square here. So this is extremely important. I will explain just later. So when you are in the part in red here, the Antigorite fraction is high enough for stress transfer to be possible upon dehydration when the material destabilizes. And when you are in the gray part here, the Antigorite fraction is low enough. And so you have an olivine network that is elastically loaded. And when you are in the part in blue here, in case of mechanical instability, you trigger a seismic rupture. And so this is the dynamic failure window. And if this is the situation at 1.1 GPa, then at 3.5 GPa, when you increase the pressure, of course, you decrease the fracture nucleation length, because when you increase the pressure, you increase the potential shear stress that can be applied in the material. So this is the first order phenomenological model that I proposed in 2017 in Nature Communications. And from this, many consequences arose. So first, here there is a fault, a high pressure fault. This is a sample they formed at 1.1 GPa, with 5% Antigorite at the beginning. You see some remnants of Antigorite ghosts, and the fault is here. This fault is 1 millimeter long. The displacement on it is 10 micrometer, and the thickness of it is less than 1 micron. We cannot really see here with a scanning electron microscope. And you can see some features that look like cracks with some material filling it, that are connected to the fault. So FIB sections were done to analyze it. So when you are close to close to the fault, but next to the fault, you see nice olivine grains. You see the talc-like phase in between, and you see iron oxide spherulites that are, because the talc-like phase does not allow much iron in its structure, contrary to Antigorite. So that's why you make these iron oxides, and you have fluid vesicles here that we interpret as vapor, because I mean H2O, because this is the other product of Antigorite dehydration. When you look at the fault, you realize that this is 20 to 200 nanometer thick, with some pockets filled with amorphous material and bubbles. I mean, the same vesicles as what we saw before. And you see when you cross this crack attached to the fault, that it contains euhedral olivine. So this is a proof of melting. The material was fully molten on the path of the dynamic rupture. This is an experimental pseudotachylyte obtained at high pressure. So this is important. So first, regarding this study, so at that time I could summarize the situation like this: the lower Wadati-Benioff plane would not correspond to the dehydration isotherm of Antigorite, but instead this is the hydration limit of the incoming plate before subduction. And when the dehydration occurs, you increase the stress, you reduce the viscosity of this, we can say it like this: you reduce the viscosity of these Antigorite clusters that may correspond to some serpentinized faults that is formed due to plate bending before subduction. And when you dehydrate this, you increase the stress distortion at the tip of these serpentinized faults, and then you increase the probability that you reach the rupture criteria. And then the ruptures occur not in the pre-existing faults, or not only, but most probably the ruptures affect fresh peridotite that is in between the faults, and that is elastically loaded. Because once again, if you don't have elastic strain stored in the rock, you don't need to release it, so you don't have seismic activity. So an earthquake at intermediate depth, at least, is elastic strain plus a detonator. Like a bomb is an explosive plus a detonator. And in between the planes, why there is no or few earthquakes, it's because there is too much Antigorite or other hydrous minerals for the peridotite bodies to be elastically loaded, and so you don't have elastic strain to release. From the lab, we can go to the field in several ways. So first, you can find, for example, this study from Marcos Cambelluri in 2017. They found in the Lanzo Massif nice peridotite blocks, massive, and all around you have serpentinites, highly deformed serpentinites that help, serpentinites help a lot to bring material to the surface. And they found pseudotachylytes inside the peridotite and gabbros, and no connection with the ductile material around. You also have other studies showing not evidence of the dehydration-driven stress transfer model, not direct evidence, but consistent observations that could account for this interpretation. You have for example, a study from Dunkel in 2017, and more recently a study from Campbell 2021, explaining the need of local stress amplifiers to account for the large stress variations during these events at high pressure. In 2018, I studied an earthquake, a fossilized earthquake in the peridotite of Balmuchia. So this is published in JGR. The fault in this case is 5 mm thick. The displacement on it is 1.7 meters. And yeah, it occurred at least 40 kilometer depth before the formation of the Alpine Ocean, as far as I understood. And you can see here in green, so the fault is in red. There is a secondary fault attached to it. And in green, this is an injection vein, similar actually to the one presented just before at the micro scale. But this one is a large one, 15 cubic meter, attached to a fault that is only 5 mm thick, right? So overall, this fault is 1 million times larger. This is the same event, but 1 million times larger than the one I described in the experimental work. So we compare a magnitude -6 with a magnitude 6 approximately, and we observe that this is quite similar, but somehow there are some differences that we want to understand. So I tried to collect all the data that were available in the literature from various studies. And I encourage you, if there are field geologists in the audience, please take values of, when you see pseudotachylytes, first you demonstrate this is a pseudotachylite. So we need a proof of melting, and then I want the thickness of it and the displacement, the relative displacement on it. Because in most studies, I found about 20 studies that report some data, but most studies didn't, I don't know. First, this is not easy to do. And then it's not that obvious from most lithologies. And then it was probably not obvious at first to think that these two parameters were key to understand the lubrication effect of dynamic melting. So here you have the displacement as a function of thickness. So A is the final thickness of the pseudotachylite, and W is the dynamic thickness of the molten layer that transiently exists just behind the rupture front. And I realized that I forgot to define what a pseudotachylite is, so I will do it now. Pseudotachylite is the rock coming from the solidification of the frictional melt. Most people say like this, but let's say the rupture-induced melt, to avoid the concepts as long as possible. And so the pseudotachylytes come from the solidification of a molten material. So pseudotachylytes have been reported in various materials and settings, both in nature and in the lab. And we know that we can scale on the field. We can do an estimate of the magnitude from the relative displacement. So if we manage to scale the thickness of the pseudotachylite, we can estimate the magnitude only by looking at the thickness of the fall, if we have a single event. So this is as you can see, most data sets follow the adiabatic trend, but some, and especially the key and pioneering study from Simpson in 1975 did not follow the adiabatic trend. And this does not mean that the study was wrong. It means that it was describing a data set in a material in which the lubrication was efficient. And as you can see here in the data of Barker, 2005, for example, at the same values of displacement, you have, at the same values of thickness, you have much smaller displacement, 1 to 2 orders of magnitude lower. And this is because the material in one case was a mafic rock and probably somehow hydrated, and in the other case it's a dry silicon-rich rock. Because what controls this lubrication efficiency, and so what controls the ability of the rupture to self-propagate, because so this is the viscosity of this process zone that exists just behind the rupture front. So this can be seen as the resolution of solving a Stefan problem. So we calculated the heat balance at the advancing front. You have to imagine that this is a magma wave, kind of. Sorry for people who don't want to use these words for this in this context, but let's imagine a magma cushion moving just behind the rupture front at the rupture velocity, but the magma does not propagate itself, only the melting propagates, right? Like a wave. And so in the end, you can when considering it as a Stefan problem, you can get a first order estimate of the relationship between the thickness and the displacement, and you can see that there is a critical melt thickness, magma thickness, at which the lubrication becomes fully efficient, and then you get 1 to 2 or more orders of magnitude in terms of displacement. And by the way, if you find injection, if you find a pseudotachylyte vein somewhere that is more than 5 centimeters thick, either it is a magnitude 9, or most probably you are looking at an injection vein. So please don't mistake the fold vein and the injection vein. So yeah, why talking about these the rupture mechanics itself? Because these works allow to check if to what extent the dynamic ruptures obtained in the lab are representative or not of the ruptures that occur in nature. Actually, they are fully representative of ruptures that have the same size, but not, as you can see in this modeling, and as shown by the data sets, this is not fully representative of the large events that, because once you reach a certain size, depending on the composition, you get a lubrication effect that you cannot really reach in the lab. So then you can go to the field in another way. You can work with seismologists and compare the acoustic signals you get in the lab with the seismological evidences. So this was the work we did with Seiko Kita in 2018. We were able for Northeast Japan to separate the upper interplane and lower events, and we realized that the B values were not the same, and we decided to study the easiest part, the one that we could understand better, because once again, the lower plane is in peridotite, and the peridotite is necessarily more simple. I mean, necessarily simpler than compared to the upper plane. Or at least the uncertainty is lower. So as you can see, for the lower plane, between the region of Tohoku and the region of Hokkaido, you can see that the B value beneath Tohoku is almost 1, when it's only 0.86 beneath Hokkaido. And the only model that is able to explain this result that Seiko had for a long time is the dehydration-driven stress transfer model. I will explain. when you calculate the equivalent of the b values, so the b value is the slope of the Gutenberg-Richter distribution, which means if you increase the b value, you increase in the proportion of small events in a catalog of earthquakes. And when you decrease the b value, you increase the number of large events compared to for a given number of small events. So if you calculate here, so here this was the b value for the real real data, I mean the seismological data, and here for the artificial samples, so the experimental b values, when we calculated for each sample, we realized that this experimental b value increases with the Antigorite fraction. So then, based on this, we speculated that this could be exactly for the same reason that we have this b value larger beneath Tohoku than in Hokkaido, and this is consistent with the existence of a denser network of serpentinized faults due to the difference in the angle of the subduction. So yeah, as you can see, the Kurile trench is parallel to the oceanic fabric, so you can reactivate faults, but this is not the case. You have a significant angle of about 50 degrees for the Japan trench, and so you have a denser network of serpentinized faults, and so you have smaller fresh peridotite bodies in between, and so you have a larger number of small earthquakes when you dehydrate the system. Same as in the sample. This is a big lab, tectonic lab. So we have a lot of seismological evidence that this I mean, we have more and more seismological evidence that this dehydration-driven stress transfer model would be accurate for the lower Wadati-Benioff plane of seismicity, at least. And we also have petrological evidence, because when we compare the dehydration kinetics of Antigorite, chrysolite, lizardite, different kind of serpentine, and other minerals, we see that all of them are very fast. All the studies that have been done in any kind of conditions have shown that these destabilization reactions are very fast, and so fast enough to trigger mechanical instability if they occur in a zone that is a complex network, for example, of serpentinized faults with fresh, elastically stressed bodies in between. I would like to talk briefly about this work from Marcel Tillman. So in 2018, he proposed a model, numerical modeling and he showed that the grain size reduction is extremely efficient for the self-propagation of thermal runaway. And what I want to add to this is that the easiest way, and John will probably agree, the easiest way to reduce the grain size is a metamorphic transformation, right? So there is something to understand regarding the interplay of this in future modeling. In a paper in Litus in 2019, I explained in details, for those who are interested, I explained in details the link to what extent our experimental samples can be compared to the serpentinized faults and also to the slab itself. All of them are populations of Antigorite and olivine, plus, of course, some more complexities, but at first order. And you can define these asperity lengths around on the serpentinized fold and also in between the serpentinized folds. So yeah. But all this is okay if you consider only the magnesium silicium hydrogen system, right? And if I mean, theoretically, if you consider this simple system, you would expect in a pressure temperature diagram that the earthquakes occur only around these lines where the material is expected to destabilize. And this is not really what we get, because if we do this, even with some kind of uncertainty, we expect just I mean, less than 20% of the seismicity of the data sets I presented before. And if we add chlorite and aluminum-rich olivine, so if we go from the MSH to the MASH system, then we can explain some more earthquakes, but still very far from the reality, right? And this is partly due to the fact that when you change a little bit the composition of the minerals, you don't have the same minerals anymore, and you don't have the same stability limits. And there are many minerals that we know and that we don't know really well the stability limits, and there are also minerals that we don't know yet and that probably exist at depth. So this is the summary of all the experimental works on Antigorite stability only. So this is Antigorite. And when you take all the different Antigorite compositions and water saturations, you realize that you are able to fit, you have a potential correlation with 90% of the seismicity data sets that that were considered by Abers in 2013. And this is what we know about other serpentine minerals: chrysotile, lizardite, amazite, and this is what we know about the potential destabilization of chlorite minerals. And also I added the chloritoid in case you are not far from a contamination from the subduction channel. So yeah, then you can play and you can add whatever you want, but you have to be careful that it still makes sense, because then you can say, you can invent that the minerals are somewhere, and each pressure temperature condition here can be fitted by at least 3 or 4 curves that go through those. So then we have to be careful with this.
Thomas, I'm just briefly pointing out, you've had 50 minutes now, so I'm sure there will be lots of questions. I'm just passing that information on. Yeah.
Thank you for that. So as I said, many phases, and the stability change with the composition, and there are many phases that we discover. Some were discovered last year and some will be discovered next year, and we don't know yet the stability of them. And also there are association between phases. For example, here, and I will try to go faster. So this is an exercise I did for the northern Chile subduction zone. So you can see that in yellow, the lower Wadati-Benioff plain, you can explain all the seismicity of the lower plane by Antigorite dehydration, and the rest you see that this is more it requires additional phases. And recently, with Elena Manea, we did a work on subduction that I didn't know about. So there is a locked subducted ocean beneath Vrancia in Romania, and so we decided to study the intermediate depth earthquakes that occur there, and to check if we see anything interesting in terms of pressure and temperature conditions. And so what we saw, first, we did we relocated in a 3D model, and here you can see the 900-degree isotherm surface just to show the shape of the remnant. And when you look at the pressure temperature conditions, you see a beautiful S shape that indicates that you are definitely dehydrating serpentine minerals up between 60 and 120 kilometer depth. And at higher temperatures, you are actually dehydrating the 10 angstrom phase. That is one of the talc-like phases. So this is really a beautiful result to me. And we can discuss about it just after if you want. And so yeah, this continues the story, never end. And to finish, probably many of you know the work of John Wheeler. He tried to review many and to discuss reactions in a broad sense in terms of numerical modeling, because this is time to do something to try to integrate it. And the most important sentence of the paper to me is reaction is a deformation mechanism. And this is something that we don't see enough in the interpretations of many papers, not only experimental. And I think that additional techniques could help characterizing, quantifying the interplay between reaction and deformation. And for example, I would try to adapt electrical conductivity measurements for several reasons. And one of these is that this kind of property is highly controlled by the shape of the grain boundaries and the intrinsic properties of these grain boundaries, and highly related to the transport properties. So there is something to do to understand the kinetics of transformations in unstable system in relatively low temperatures like this. And so this is the last slide. The main take-home messages are: an earthquake is not the trigger of an earthquake. I mean, it could be in some cases, but we have to distinguish earthquakes, their seismic rupture, and the trigger of the mechanical instability. And we can study these separately. Intermediate depth ruptures are not that different than conventional ruptures, let's say. A myriad of other transformations can trigger seismicity, but serpentine and talc minerals are responsible for most ruptures. We are not talking about thermodynamic equilibrium at any point of this talk, and complementary methods always brings new insights. It is time to think about an integrated modeling framework to constrain the interplay between mineral transformations, stress percolation, and strain localization. And thank you for your attention.
Yeah, great. Thomas, thank you for that. That was very wide-ranging talk.
Yeah,
I think the plan is yeah.
Sorry.
Janine, is the plan we take Liverpool questions first, and then do you have some typed questions from YouTube people?
Yes. If there's any questions from people here, we can switch between the two. So
yeah. Okay. Well, let me throw it over to Liverpool people first. But if if not, then Janine, why not just get the YouTube people involved then? Yes. I mean, Thomas, you'll know I have lots of questions, but I'm not going to go first.
Yeah.
Okay, Dan has his hand up, John, actually.
Oh, right. So, Dan, just say it with words in the old-fashioned way. Dan,
Hello.
Okay. So, yeah, thanks, Thomas. That was really great. It's good, interesting stuff. So, I had a couple of questions. To start with, the nucleation length that you looked at before, quite early on in the talk too. So you had beta over mu, and then G over the shear stress squared as well. So are you incorporating the shear modulus and the bulk modulus into so what's U and G in that equation? I've not seen. Yeah, sorry, what mu and G is. Yeah.
Oh yeah. Mu is actually the rigidity of the material, right?
Yeah. Okay. So that's shear modulus. So G would then be.
And then the G is the Griffith
Okay.
criterion. I don't know how. I don't remember how to call it, but
okay. I see. So yeah, it's written in a slightly different way. So presumably the nucleation length is a really small value, so it requires a large stress drop. Is that right?
It's not about the stress drop.
Yeah.
It's not necessarily about the stress drop, but at least about the shear stress. Yeah, the shear stress level.
Yeah, I mean, you know, but the shear modulus is obviously going to be quite large. If G is the Griffiths energy release rate, that's you know, usually in megapascal seconds or something like that. I can't remember.
Yeah. We actually
So you know, I mean, so you're saying that your nucleation length is basically comparable to the spacing of these the olivine that you've got in the materials. So if the nucleation length
yes, in some conditions it can match. Yes.
Yeah. Okay.
Depends. Yes.
So the stress drop would have to be pretty large then, really. It's not going to be on the normal kind of 1 to 10 megapascal.
No. This is quite significant. And there are a couple papers, recent papers that I saw recently published that show that there are natural evidence of stress drops that are on the range of 1 gigapascals. You know, for large for great depth, if you have 2 gigapascals of confining pressure, this is not a problem.
Okay.
I mean, to some extent it could be a problem, but yeah. So we took the fracture. So G is to be clear, this is the Griffith fracture energy that we took in the calculation, equal to 1 joule per square meter.
Yeah. So it's joules meters. Yeah. Okay. Yeah. So you know, just related to that, if the nucleation length is very small, you mentioned later on in your talk the relation of the experiments to the field, and you talked about the scale in the field being on the 10-meter scale, the variability that you have there, whereas in the lab it's on the kind of 10 micron length scale. So you know, I guess the nucleation length is a nucleation length, so it wouldn't vary. It would be the same in the field as it is in the lab as well. So
yes, you're right, and you're not the first to ask this. I mean, to notice it, and I think that at the time I wrote this paper, as I was at the scale at which I got the results relatively compatible, when I did the calculation. I took the nucleation length, and it worked in this model, and then I extrapolate this model, but it's probably because the nucleation length is proportional to something else that is more relevant for the thing, but as long as the model explains some part of what you are trying to understand, which was actually why it was working with 5% and not with 20 or 0%. As long as the model explains this, then we don't ask the model to be fully describing something real, right?
Cool, that's great, thank you. I'll go back and read your Lithos paper as well, I think so.
But I would be happy to go further in this direction, because I know that my model is could be improved, and yeah.
Cool, that's great, thank you.
Step by step.
Yeah.
Do we have other questions, shout outs from Liverpool first of all?
I have a question, John, if that's all
you
right.
do, your hand is up, I can see it.
Digital hand up, yeah. Thank you, Thomas. I really enjoyed your talk. It's quite a different topic for me, although I was struck by some similarities with my own work, because I'm looking at magma propagation and the development of volcanic plumbing systems. And what we do there is that we make this assumption, or we sort of pretend like things are already moving, and we don't really think about the inception of the crack in which the magma is being transported. Mm-hmm. And we have a lot of question marks at the bottom of our plumbing systems. And so I wondered what you thought about how applicable some of the concepts and ideas in your models could be applied to magma propagation, which then goes on to feed like a volcanic plumbing system. Is there any overlap there? Some of the models and things seem quite familiar to me, although the context is quite different.
Yeah, I saw a paper just recently. I saw a paper just published in Nature Communications a couple of days ago, I think, about this mush concept, and how we think the melt percolates, because I would say that the main melt transport would be a grain boundary percolation. This would probably be applicable for a certain depth, or let's say pressure to pressure window, but yeah, when you are very close to the surface, probably the cracks take part of take a significant role in the transport in the balance. But I don't think that what I do could be applicable to understanding how magma ascent occur, for example, in the subduction system, but the contrary, yes, because in my understanding, I will show in my understanding, this process zone that I try to understand, this process zone is a magma. It's not a magma chamber, but it would be to some extent an extreme end member of a magma chamber. And I found in Balmuchia, in this in the fault, in the magnitude 6 fossilized earthquake, I found in injection veins chemical gradients and very, very beautiful olivine and pyroxene. This is a peridotite, fully molten, and then you have these tension cracks that open in the dilatant quadrant and that are directly able to suck the magma out of the fault core. And this is fully described in my 2018 paper. And this has triggered actually troubles with my co-authors at that time, because I said, no, you cannot use the word injectite or injection vein, because the material is not injected. It's sucked out of the fault core because you have tension cracks that open. And depending on the viscosity of the magma, so it's extremely efficient in a peridotite because the viscosity is very small, especially with the 1% H2O that I had also. So why do I tell the full story? Yes, I have something that I call fractionated crystallization in some injection veins that are some centimeter long. I have at the tip of it, I have amorphous material in some pockets that are fossilized inside some shocked pyroxenes. I still have pockets of amorphous material that has a composition that is close to a bitonite, because on the way the melt migrates through the tension crack, then you crystallize micrometric olivine and pyroxene, and so the composition of the melt goes in the end close to something that like a feldspar. And it was really difficult to understand at first, and in the end we still have some kind of debate, because they say, okay, yes, but if you think at pressure in terms of relative pressures, then you can still say this is an injection vein. I say, no, this is not. Because if you say injection vein, then it means that you have overpressure in the fault. But do we know if we have overpressure in the fault?
Oh, it's really interesting.
Especially if the process zone viscosity is extremely small, and if it can directly be sucked very fast by the tension cracks, then I would not expect overpressure.
Great, thank you.
I
did not exactly respond to your question, but
I think
yes.
it's a nice discussion, and I learned a lot, so thank you. And I'm going to read.
So you know the word tachylite at first,
yeah,
because tachylites don't exist, right? But at first we thought it existed, and they were considered as volcanic rocks. I mean, magmatic rocks, and they were not me, because I was probably a bit too young, but when tachylites were described some decades ago, for example, in Palmuccia, then it was believed that it was related to a super volcano or something, and there is still some explanation on the road about this, and this is funny actually. But so step by step the concepts evolve, and that now we have pseudotachylytes that we can describe, and we have proof of melting. But it doesn't mean that the people who were describing tachylites were wrong. They were just on the way to understand pseudotachylites, and they understand before that it was a magmatic process. Because in the end, within a couple of years, I think that we will, or maybe 5 years, I think we may step back a little bit and consider again that pseudotachylites can be considered as a n-member magmatic process.
Great. Well, that's really interesting. I think Caitlin, there's a question on the YouTube. She's going to ask. Go.
Yeah,
Oh, yeah, go ahead. Yep.
there's a comment on YouTube from Stefan who says, I think it's important to point out for people who observe PT in the field that the thickness would be the average melt per unit fault surface, including the injections and main fault veins, unless Thomas disagrees. I don't know if you have a response to that comment.
So, yes. So, when you have, so of course, when we measure on the field, we measure the final thickness of the pseudotachylyte, and this is usually, for example, twice thinner than the actual dynamic thickness of the molten layer we estimate for the lithologies I studied. But it's on the same order of magnitude, because even if you have a population of injection veins, the volume they are able to suck is does not reduce the thickness of the pseudotachylyte by several orders of magnitude. And I may need you to repeat the question to see if because there is some part I'm not sure I understood.
Yeah, it's important to point out for people who observe PT in the field that the thickness would be the average melt per unit fault surface, including the injections and main fault veins.
Yeah, I have nothing to. Yeah, this is correct.
Okay, thank you.
You see, I can answer questions very fast, but I don't. This is a problem.
Caitlin, the more YouTube questions, or shall we move to the next into the egalitarian?
Yeah, there's nothing else on YouTube.
Okay, so what we'll do now, I mean, I think, Thomas, you've got the link, haven't you? So we just move into a different room and chat for a little while there as well, yeah? Okay,